Okay, so today we will get into section 13.2, vectors in space. So the previous section dealt with vectors in a plane, which way you can think of it in the XY plane. But now we're going to take a look at vectors in the XYZ space, right? No longer a plane, right? So think of something like this, right? So what you're looking at is the standard kind of way that we, at least when we try to draw them in a two-dimensional plane, essentially, three-dimensional space. So what you're looking at here, the axes in red coming at you or towards the screen, right, is the x-axis, the one that is kind of horizontal there, and the backing is the y-axis, and the blue one going up and down there, vertical, is the z-axis. Right, so usually here we'll take in here, I am terrible at these drawings, which is why I will rely on the GeoGebra drawer. They usually here are right-handed rule, where you think of if you take your hand, right, and you stick it out the X, and then kind of your right hand, and then you curl your fingers. That would be the direction of the positive y-axis, and then the thumb pointing in the positive z-axis. Right, so here, just so we get an idea here, this would be like 1, 2, etc. Back here would be -1, -2, and then here we'd have 1, 2, and here -1, here 1, and then going down here -1, etc. So that looks like a jumbled mess, but if you see here, this is much better. All right, so you see here that we're the positive side, and then the negative side there. Now the equations for solids, or surfaces, I should say, in the XYZ plane, we can kind of use our intuition of what we know in terms of the XY plane to kind of figure out what some of these surfaces are going to look like. Now let's take a look at first. We can think of different planes that make up this space. Now, if we think of the XY plane, right? So this describes all the points the XY plane. What that means is that Z is equal to 0. Right? So that would be it would be essentially a plane, our two-dimensional plane, and here our XY plane, like we're used to working with when we're dealing in R2. So here, if we said, simply write, what happens when Z is 0? That means what we have describing here, what you see there, is the XY plane. All right, and then similar, that's not the only plane that we have here. Well, what about the ZY plane? Right, when does that occur? That occurs where we have values of Z and Y, and the other variable X is equal to 0. All right, and again, looking at this here, well, let's say, all right, what happens when X is 0? And again, right, the way you want to interpret that, when X is 0, what that is telling you is that, that means that the other two variables, Y and Z, they could be anything. And there you could see, while it's a plane, you can think of that plane actually as a collection of ordered pairs, right? That what they all have in common is that their X coordinate is 0, but Y and Z can be anything else. All right, and then similar, the third plane, and the third basic plane, I guess, we can, as we'll see, we can actually draw or come up with equations of all different planes, and that'll come in a later section. But here, the other plane is the XZ plane, and that would be when Y is equal to 0. All right, so think of a plane as a collection of ordered pairs, and that they all have in common is that their Y coordinate is equal to 0. Okay, and you see those three planes there. Let me okay, you see there the XZ plane, where Y is 0, and again, think of these planes as collection of points. All right, okay, Alright, now, in terms of, now here when we think of kind of, we're almost, when we go from R2 to R3, we're kind of going up in dimension. So if you think of, all right, when I'm in R2 and I have an equation where it's just like x equals 0 or x equals 1 even, what does that correspond? It corresponds to a line, right? Instead of a two-dimensional flat plane, one-dimensional object. So the same thing here, right? When we have z is equal to 0, right? That's going to correspond, if we're in R3, into a two-dimensional object. In this case, that two-dimensional object being a plane. All right. Now, how do we plot points? So again, let's look at what did we do in R2. In R2, if we were to plot, let's say 1, -2, it was almost like, it was an ordered pair. It was essentially a set of directions, right? It said, all right, in the x direction, go 1 in the positive, 1 in the positive direction, and -2, go 2 in the negative direction. All right, so plotting this here, that would be, okay, 1, -2. And we would have that. So it's the same idea in R3. R3, right? We won't have an ordered pair. What we'll have are ordered triples. R3, we have ordered triples. Okay, so we'll have something like x, y, z. So same thing, think of it like a set of directions where it says, all right, x direction, y direction, z direction. So for example, we have 1. Let's say we had something like this. All right. Okay, so that tells me go 1 in the positive x direction, -1 in the z direction, and then -1 in the x direction, -1 in the y direction, and then -4 in the z direction. So if we look here, block these out here. Okay, so here we have 1. All right, looking at that there. So 1 in the x direction, then -1 in the in the y direction, and then the -4 down along the z direction. So kind of graphing that. 1, -1, 4. -4. Okay, and then you can see that happening down there, right? So here, looking at that. All right, now looking at it right from above, you can almost see, like, think of it like flat, right? Like the XY plane, and you could see there that 1, -1, and then adding the depth of the Z, you can see, all right, it goes down 4 units. Okay, so that's kind of how you want to interpret these order triples, right? It's always X, Y, Z. So it tells you how many to go in the X, then the Y, then the Z direction. Okay. All right, so we have here order triples. We saw the XY, the XZ plane, and really kind of to expand on the whole plane idea, you can really, looking at just basic planes where we have equations in one variable, right? If let's say we had x is equal to 2, again, what does, so what this is describing, again, I want you to think of these as collections of points, right? Sets of points, right? So what would if x is equal to 2, my equation, what would a point that satisfies this equation, what would it have to look like? Well, it's telling me, well, x has to be 2. But what do y and z have to be if they don't show up in the equation? Well, they can be anything you want them to be, right? The only thing that is required, these can be any real numbers. Now, if we were in R2, we wouldn't have that z component. It would just be y could be anything. So we would have a, we would have a vertical line, right, that goes through 2. right? Since y could be anything. Now we are up one dimension, so if we're in R3, we have y and z could be anything. So we have not a line, but in this case, a plane. Right, so looking at this here, and let me plot x equals to 2. Right, and now you can see, there we go. Right. Collection of all the ordered pairs that have 2 for the x coordinate and any other values for the y and this e coordinate. Or then we can see that if we let's just pick one, right? 2, that has to be true. 1, -2. Right, let's choose another one here. Another point. Again, 2 must be in the x coordinate, so let's do 0, 3. All right, and you can see there, if I move this plane around, they are part of that plane. All right, so there we see equations of simple planes. Okay, so those are just kind of the basics of the of plotting points and just our three-dimensional space. So now what we want to kind of focus on here are, well, what do vectors look like in 3 dimensions? Right. So here are vectors. Again, remember in R2, in R2, we had something like vector V had 2 components, V1, V2. All right, and again, the vector is something that has magnitude and direction, and the same thing in R3, right? That is across R2 and R3. All right, so we describe a vector like this in R2, and in R3, the same idea, right? We just are up one dimension. The vector V would be V1, V2, V3. Okay. All right. So now let's look at also in R2, the magnitude of V is equal to square root of V1 squared plus V2 squared. Okay. Now, does that hold? How do I do the magnitude in R3? Remember that in R2 we arrived at that formula using the Pythagorean theorem, and we can actually do the same thing, arriving at it using the Pythagorean theorem, but now it's a little more, since we are in 3 dimensions, we can come across here at a bit still using the Pythagorean theorem, but now it's in 3 dimensions. So we, well, let me show you guys a picture here. Oh, there we go. All right. Okay. So if we look here, we look at this vector P here, and again, I gave it a value, but just assume, in fact, let me, let's do this here. All right. Go over to our notes here. Okay. So, okay. So let's try to derive a formula here for the magnitude of a vector. All right, so we have some, let's say P is just some arbitrary point, V1, V2, V3. All right, and then here, similar, the vector V, remember, P I'm treating as a point, V1, V2, V3, as opposed to the vector V, that is the arrow that you see, that is the vector in standard position, right? Here in standard position is at the origin. So the origin, in R3 is 0, 0, 0. Okay, so the vector V is this one right here, V1, V2, V3. Oops. All right. So we would like to find here the magnitude or the length, in other words, L, right? The length of that vector, we'll call the magnitude of vector V. Okay. All right. Now we see the point Q, R, and S along with the origin. Now again, looking at this, the point Q is on the x-axis. So Q, all right, on the x-axis, and here we'll just call it V1. Again, I want to keep it as arbitrary as possible, even though it looks like I did give it a value in my graph there, but let's just assume it's just some value V1, right? If it's on the x-axis, that means that the other values are 0. Okay. And now for the point S, that is on the y-axis, and that would have value 0, V2, and 0. Okay. Excuse me. Okay, and then from here we have the point P is right there, V1, V2, V3. Other point we see there is R, and that plane that you see there is in the XY plane. So in this case, that would be V1, V2, and then Z would be 0. Okay. Now, if we think of here the triangle formed by that L and also this line segment, PR, so that is a line segment, and also the line segment OR, that is a right triangle, right? If you look at that, right, that is straight down, right? So it is in fact a right triangle. So I can rewrite using the Pythagorean theorem, the magnitude of V, or L, right, whatever we want to call it. Here I'll use the vector notation, is the same as the OR, the line segment, the length of that squared, plus RD squared. Oh, sorry, I have not RD, PR. PR squared. Right, so that is from the Pythagorean theorem. All right, now if I go further here, we could say, all right, well, if I look at that triangle in the XY plane, right, the one made up by the segments OQ, right, so this one here would be OQ, and then this one here would be QR, right, I have another right triangle there in the XY plane. Right. Well, that means that what we have there, we have OR is the hypotenuse of that right triangle in the XY plane. So OR squared is the same as OQ squared plus QR squared. Right, so here we have excuse me, not vectors, line segments. Plus PR squared. Okay, and if we find the distance from O to Q, looking at that there, well, that's just a straight line. That is V1 squared. And the distance from Q to R, again, that runs parallel to the y-axis, so that would be V2 squared. And then PR, that again runs parallel to the z-axis, so that would just be the height of it, which is V3 squared. Right? And we have a nice result here where the magnitude of V is equivalent to the sum of the squares of the components, right? V1, V2, V3. You add them up, and then you take the square root, right? So it's a nice little result because now it's just analogous here to our result in R2. Right? So to find the magnitude of a vector in R3, it's just the square root of the sum of the squares of the components of each vector. Okay, so for example, if we wanted to find for this vector, then we would have one squared plus 2 squared plus 3 squared, and that gives me square root 14. All right. Okay, so that is how we find the magnitude of a vector in R3. Okay, now another kind of equation I want to go over in our R3 space is that of a sphere or a ball. So how about we'll start with, again, the R2 equivalent, that being the circle. So a circle of radius r centered at the origin would have this equation. Right? Circle radius r centered at origin. Right. Now if it was centered at some other point, let's call it HK, then that would be this, right? Again, still with radius r. Okay, so as it turns out, that same formulation it holds in R3. Now, in 2D, it's a circle. In R3, we have a sphere. So a sphere centered at ABC with radius r has equation x minus a squared plus y minus b squared plus z minus c squared equals to r squared. Okay, and then here, let me show you this here. Okay, and then we see here that is a sphere of radius 4 centered at the origin. Right, and again, you can, in this case, A, B, and C are 0, but we can always play around or change the center. You can see that moves it in the appropriate way, right? For something like this, as you see the equation, the center would be 2 comma negative 2 comma 1. Right? And then you could see that right there. Okay. Now, the way you want to think of a sphere, right, that is just the points that are units away from the center. Okay, so that's what equality, right? If you think of it as a set of points, it includes all of the ones that are on the boundary of that sphere. All right. Now, if I change, let's say here, x minus a squared to an inequality less than or equal to r squared, then what we have here is a ball. All right. So this set not only includes the boundary, but everything inside the sphere as well. All of those will be part of this particular set. Okay. So the ball includes all interior points as well. Okay, so let's look at an example here. Let's say that for this example, I would like to show the equation below represents a sphere and find its radius. Okay, so let's say we had this equation. So I want you to show that this is a sphere, and I want you to determine the radius of that sphere. Okay, now the way we're going to show this is that we want to show that it follows this format here. Okay, the format that we see right here. Okay, so let's start. First thing I want to do here is I want to move the 4x and the 2y to the left-hand side of the equation. So we'll have x squared minus 4x, and then y squared minus 2y plus z squared equals to 0. Okay, now I notice I left a space after the 4x and after the 2y. The reason for that is that I want to factor those into perfect squares, essentially, into something that looks like this, x minus something squared. All right, and the way I'm going to do that is by completing the square. All right, so to complete the square to something like this, we take whatever coefficient is in front of the linear term, in this case 4. Don't worry about the sign. the sign will come into play next here. So here, excuse me, one mistake here, that should be plus. Okay, all right. So take half of 4, which is, and it's always plus 2, whatever half of that number, in this case 2, and then square it. All right, but again, this is an equation, so whatever I add to one side, I have to make sure to add to the other side. So I'll add 4. All right, 2 squared. Okay, and then here we have 2, so take half of 2, and that is 1, and square. Okay, so now here we'll add 1. Excuse me. Okay, so now we have this, and now what we're going to do here is I'm going to factor this. All right, so here. And this turns out factors into, now we use the minus, x minus 2 squared plus y plus 1 squared plus z squared is equal to 5. Okay, and now we have it in the sphere form, right? So this is showing that it is a sphere, getting it in this form. So this is a sphere, center at 2, -1, 0, radius of √5. All right. Okay. So let's move on here to, let's try a different example here, still dealing with spheres. So for this example, I would like to find an equation of a sphere if one of its diameters has endpoints (2, 1, 4) and 4, 3, 10. Okay. All right. So the diameter, right? So that means that the point 2, 1, 4 is on the surface of the sphere. One of them is, and then another point is on 4, 3, 10, right? And then when you connect those 2 points, they go through the center of the sphere, right? Let's look at a visual of this here. So how about, okay. Okay, here you go. Okay, so we have P and Q. All right, so what you see there are those 2 points, right? And I'm going to connect both of those here. Okay, so that line segment that you see there is a diameter, right? And again, similar in R2, when we think of a diameter, we think of that being as twice the radius. And that is the case here, right? It's a diameter, so it's twice, even though it's a sphere, right? That means that the diameter is twice the radius. All right, so what that means is that, all right, the radius is essentially the midpoint between P and Q. Since it is a diameter, the radius is the midpoint of PQ. All right, and again, similar to in R2, the midpoint, you can think of a midpoint almost like the average in all three directions, right? If you recall in R2, actually here, let me change up my color here. If we have 2 points, the midpoint is this formula right here. All right, and you can almost, I mean, it's essentially an average, right? Average in the x direction, average in the y direction, and that coordinate is the midpoint of the line segment between x0, y0, and x1, y1. All right, and that exact same thing translates into R3. In R3, right, given x0, y0, in this case now z0, and x1, y1, z1, the midpoint is just the average in all three directions. Okay. All right, so now let's go back here. So let's find the midpoint, and what the midpoint is going to be, that is going to be our radius for our circle, or excuse me, the center of our sphere. Sorry, that was got both of those mixed up there. So here, the center of sphere is the midpoint of the 2, 1, 4, 4, 3, 10. Okay, so let's call it C, and we'll take for the center, so C is the point 3, 2, 7. All right. Okay, let's plot that over here just to see that. What was it again? 3, 2, 7. Looking at that, that looks about right. Just eyeballing it there, right? But oops. All right. Okay, so that looks good here. Okay, so I've at least found the first part of how to do, or the one of the parts that I need for the equation of a sphere, right? I need the center. The other thing I need is the radius. All right, so I can find this a couple of different ways here. I can think of the vector from P to Q and then find the magnitude of that, and then take the half of it since it is a diameter, or I can just think of the vector from P to C, or Q to C if you want, and find the magnitude of that. Okay, so in doing that, we could say, all right, that is here, square root. Remember, since this one is not in standard position, what we do there is we take here the difference between the x components. So we'll take here, the center is 3, and then for our point P, here, let me PQ, 3 minus 2 squared, and then 2 minus 1 squared, plus 4, 7 minus 4 squared. Okay, and we get there square root of 11. Okay, so now I have all the components for my equation. So the equation is x minus 3 squared plus y minus 2 squared plus z minus 7 squared equals to 11. All right, and let's confirm that we have that is correct. And let's just type that in here. X minus 3 squared plus y minus 2 squared plus z minus 7 squared equals to 11. There we go. All right. Found exactly what we were looking for. Okay. All right, so let's move along here and let's define our vector operations in R3. And again, very analogous to the vector operations in R2. All right, so vector operations in R3. So let's say that we have two vectors in R3. Let's say vector U has components U1, U2, U3, and vector V has components V1, V2, V3. All right, so U plus V is going to be done component-wise. It's similar to the way we did this in R3, excuse me, in R2, where if we had something like this, the way we would calculate this would be to add the x components together, the y components together, and the z components together. All right, and then the same thing for the scalar multiplication. If we add C of U1, U2, U3, all right, we will take that scalar C, and again, C is just any real number. And we will multiply it by U1, multiply it by U2, multiply it by U3. Okay, so those are the operations in R3. Again, just that extra component in the Z that we have to take care of, or that we introduce here. All right, and then similar in R2 when we had unit vectors. All right, in R3, our I hat now becomes the vector 1, 0, 0. All right, the vector j hat is now the vector 0, 1, 0. And now, since we are in R3, we introduce the third one, k hat, and that is the vector 0, 0, 1. All right. Okay. All right, now these three vectors, I hat, j hat, k hat, very important. Again, if you've taken a linear algebra course, and if you haven't, just kind of brief this. I'm not going too deep in the weeds here. These are what are known as basis vectors, which means that we can write any vector in R3 in terms of I hat, j hat, and k hat. All right, so for example, let's work through some of the mechanics here of doing that. Let's let the point P (5, 11, 12) and Q be the point 1, 14, 13. So I would like to express PQ in terms of the unit vectors. Vectors I hat, j hat, and k hat. All right. And then from there, after we do that, let's find the magnitude of PQ. Okay. Okay, so let's start first by finding PQ in kind of standard position here, right? So 1 minus 5, 14 minus 11, and 13 minus 12. So that vector would be -4, 3, and 1. So that would be the vector PQ. All right, now writing this in terms of the base or the unit vectors I hat, j hat, k hat, very similar in the process in R2 where we turn the x component to the coefficient of I hat, the y component into the coefficient of j hat, and then the z component into the coefficient of k hat. Right, and performing this operation as defined in R3 returns to us the vector -4, 3, 1. All right. Okay, so that is part A. And then part B, to find the magnitude of PQ. Okay. We have square root of -4 squared plus 3 squared plus 1 squared. Okay, and that gives us here 16 plus 9, 25 plus 1 is root 26. So that is the magnitude of that vector from P to Q. Okay. Okay, so let's move on here. And the last thing here is this idea of a collinear. All right. And now the idea of collinear is that collinear. So points are collinear if they all lie on the same line here. All right, now if we are in a plane, right, it's kind of easy to see, or we can derive an equation here to, and then we can just plot it, and we can say, all right, does it go through all 3 points? All right, and really, if we have any 2 points are always collinear. All right, but the third point is where now it becomes a little tricky, right? How can I tell if 3 points are collinear? So, for example here, and now we're not going to be in a plane, but we have our 3-dimensional space, right? We have, okay, example, determine if P, Q, R are collinear. Yeah. P, and that would be 1, 6, -5. Q, that would be the point 2, 5, -3, and R, 4, 3, 1 are collinear. Okay. All right, now I can do this by using vectors. So what I'm going to do is I'm going to say, all right, I'm going to look at the vector PQ and PR. Okay, and what I should have, if they have the same tail here, they should be in the same direction. All right, and then I could just kind of extend that vector out and it would be on the same line. All right, so I'll start off by saying, all right, what does the vector PQ, or what is the vector PQ? So that will get 2 - 1, 5 - 6, and then -3 - -5. And that gives me 1, -1, 2. Okay, and now let's take a look at the vector PR. All right, and that is going to be 4 - 1, 3 - 6, and 1 minus a -5. And that gives me the vector 3, -3, 6, right? Now they're not equal, but that's not what I'm looking for, right? I'm looking for in the same direction. So here, any scalar multiple of 1, -1, 2 will be in the same direction. And notice here, I can factor out a 3, right? It's just the equality of scalar multiplication. And we can see, all right, the vector from PQ and PR, right, with the same kind of tail, they're in the same direction. So what that tells me is that P, Q, and R are collinear. Since the vectors that start with the tail P are all going in that same direction. All right, let me bring up a picture here. Okay. So we see there are those points, P, Q, and R. All right, and you can see just kind of looking at them, it says, all right, it looks like I can draw a straight line, but again, here it's kind of hard to draw. I just kind of eyeballing it here. All right, so what the calculations that we did were the vector PQ. We calculated that, and then we did the vector PR, and we determined that they are in the same direction. So that meant that I could come up with, or I could find an equation that included all 3 of those points. Right, and that is that equation, and here you see the graph, which is a collection of all those points that are all in that same direction of 3, negative 3, 6. Now, we'll talk more about how to come up with these equations of lines here in a later section, but now you can visually see, all right, if the vectors are in the same direction and they're both starting at P, then there is definitely a line that goes through P, Q, and R. So they are, in fact, collinear. All right, that covers 13.2. Thank you.